Swayam Prabha. Digital India. Educated India.
So in the last lecture of mine, we were talking about the cash organization, and we were trying to go through this little quickly. Most of you know about the set associative cash organization, so I'm not going to go into the details of this. But what we are trying to do here is that we are trying to look at set associative cash organization as the most general form of cash organization, and then you can look at direct map to cash as a set associative cash with an associativity of 1, or you can look at fully associative cash as a set associative cash with one set and all the lines in that to be mapped to the set. Okay, so that is fine, but why are we talking about cash organizations and what is its relevance to compilers, you may ask. So for example, we can talk about certain compiler optimization which would improve the cache hit ratio in your program. In order for us to understand that, first we need to understand how do we actually calculate how many cache misses or hits would be there in a simple program, right? Of course, there are when you have multiple levels of hierarchy and associativity and things could become harder, but at least some simple exercises we can do in order for us to understand issues about locality and access recency and things like that. So in order for us to do that, let's just look at cache organization in some level of detail and then try to understand how things work. In this exercise,
Sir, there is a question. Sir, yeah. Sir, someone is asking, Aditya is asking, how do we ask questions? Do we want to save them for the end, or do we want to...
Okay, what I will do is that I will give you time after every half an hour or something, a session for about 2-3 minutes for question answers. Okay. That way it would be easier. I am not looking at the chat window, so I wouldn't find if you're posting something there. Right?
That's fine, sir. What we can do is we can do this every half an hour. We can do this question answer.
Correct. Right. So please hold on to your questions, and I promise to answer them either now or at a later point in time. Okay. So let's try to understand this. So let's just take a very simple case. I'm going to consider a case in which the cache has either a 4-way set associativity or, let us say, a direct map to cache. In this particular example, what I am considering is that I am considering a 16 kilobyte cache with a 32 byte cache block size and 4-way set associativity. So many of you know how do you take this address and then divide it in terms of the different fields of the accesses. So because you have 32 bytes of cache block size, there will be 5 offset bits. And if it is a 4-way set associative cache, then you can quickly calculate the number of sets in the cache, and after some calculation you figure out that it is 128. Therefore you require 7 index bits to index into the cache, and the remaining are tag bits. If it is a direct map to cache, then you would have 512 blocks or lines in the cache, and to index that you would require 9 bits, and therefore the tag bits would reduce to 18 bits. The offset bits would remain the same because the block size is still the same. So when a processor is trying to access a memory location, that address is divided in terms of the tag, the index bits, and the offset bits, and then they are used to find out whether that particular block is there in the cache or not. This also determines whether you are going to get a hit or a miss, or which accesses are going to map to the same set or to the same block in the cache, and therefore whether one would replace the other or not. So in order for us to do such kind of an analysis, let's just look at a simple direct map to cache, the same parameters, but just look at the simple direct map to cache of 16 kilobytes with a 32 byte block size. Right, we will look at several examples and then try to understand which of these accesses kind of cause a hit in the cache, and which of these accesses cause a miss in the cache, and are these misses happening because of conflict, or these misses happening because of capacity? What can be done to improve them? These are important from the perspective of compilers, so that compiler can do certain optimization to your program. I'm going to take a very simple example and then run this through quickly. I have additional examples in my slides, which I will leave it for you to go through at some point in time and understand. I won't cover all of them. Okay, once again, we are taking the addresses and then dividing it to 3 fields. And because we are talking about a direct map to cache, there are 512 blocks in the cache, and therefore there are 9 index bits and 5 offset bits and 18 tag bits. Okay, now let me just directly jump into the example. Here I have a simple loop where I have an array of 2048 elements, double precision. Okay, each element in the array is 8 byte long, and I have 2k elements, and I'm just going through a simple loop trying to add all the elements in the array. Okay, now to do this analysis, let us mainly focus on how the accesses to the array A of I is going to be and whether they cause a cache hit or a miss. Obviously, there are also other variables which are also going to reside in the cache, but for simplicity, let us not consider them. Let's only consider the accesses to the array. Right, this is the program in assembly language that is equivalent to the C program that you see here. And all that we are going to focus here is on this particular load instruction, which is trying to load the different elements of the array. Okay, now let's see what happens, right? Now, as I mentioned, there are these accesses to data, but let's only focus on A of I, okay? And in this particular example, you see that the array elements are going to be accessed from A0, A1, A2, A3, A4, sequentially all the way up to A2047. Okay, so essentially you are going to load A0, A1, A2, A3, etc. all the way up to this. Okay, in order for us to do this analysis, you have to somehow assume, okay, if it starts from a particular address, what happens to all the accesses? The starting address itself per se may not really matter much, because if you have a large enough array, then you are going to traverse through the entire cache. So it doesn't really matter where you start, but for the sake of simplicity, we will assume some address as A000. Right? You could have assumed any other address as well, and you could do the analysis in the same way. Right? Now, this address in a 32-bit format would look like this, and when you divide this in terms of the tag bits and index bits and offset bits, they get divided in this following way. I'm particularly interested in the index bits because that tells you to which cache line it is going to get mapped to. So in this particular case, this says that this is going to get mapped into cache line 256. And each cache block or each block in the memory is 32 bytes long. And in 32 bytes, I can actually store 4 array elements. So A0, A1, A2, A3 can reside together. A4, A5, A6, A7 can reside together, and so on. Right? So 4 consecutive array elements fit into one cache block. So if I look at array elements A0 to A3, their addresses or their index values, if you look at it, they would remain the same, whereas their offset bits would change. And this essentially shows how it changes from, let me just look at these last 5 digits from 00000 to all the way up to 110000. These would correspond to the 4 array element values, assuming each array element value is 8 bytes long. Okay, so you can see that this is 0, this is 8, this is 16, and this is 24. Roughly speaking, right? And they will all be in the same cache block. That is, if you keep saying that if I add 8 to this value, how will it change? It will change to 8, 16, 24. And then after that, when it becomes 32, this will go to the next value. Okay, the next bit. Okay, the index will change from 256 to 257. Okay, so for example, A4 to A7 will be in index, will have an index 257. Okay, you can do the math later slowly so that you will understand, but all the details are there in the slide so that you can actually look into that. Okay, so what happens really? Now, if I try to list all the elements in the array which are going to be accessed, their addresses are going to be something like what I have shown here, right? And they will they will get mapped to, let's say, index 256, then 257, then 258, etc., all the way up to 511. And after that, the next set of locations will get mapped to index 0, index 1, index 2, etc. And all the way it will come back to 255. Why does it come back all the way up to 255? Because you have 2K elements. Each element is 8 bytes long, and therefore totally you have 16 kilobytes. Your cache size is also 16 kilobytes. Therefore, you see this thing nicely wrapping around and coming back to the same place. If you had a larger array, for example, 4K, then it will wrap around twice and then it will come back to the same location. If you had only 1K elements, then you will only go from 256 to 511. So depending on the size of your array, you are essentially going to cover either all the indices in your cache block or some of them, or maybe all of them multiple times. So it depends on the size of the array. Now let's see what happens to each one of these accesses. When you try to access A0 for the first time, because it is not there in the cache, it's going to result in a miss, right? And this miss is typically what is called as the cold miss, right? Whereas when you try to access A1, because the cache block consisting of A0 was brought, and along with that all the other three elements were also brought in, A1, A2, A3 will result in hit. Similarly, A4 will result in a miss, but A5, A6, A7 will result in a hit. So if you look at the entire thing, right, then out of these 2K elements, right, you will have 1/4 of them as misses and 3/4 of them as hits, right? So that's very easy to calculate in this particular example. If you change the address to some other address, these locations will change, but then this calculation may not change much, right? Particularly if you assume that it is aligned to the cache line boundary, then nothing really would change, right? So what have we done? By doing this analysis, we found that in this particular program, right, the hit ratio is 75% and the miss ratio is 25%. Okay, we are always going to look at a large number of accesses. So one access this way, that way, is not going to really change a lot of things, right? And you also see that the hits that you get here is because of the spatial locality, because you are trying to access adjacent elements, right? That's really what is happening. And the misses that you are incurring is something that you couldn't have avoided, because you have to bring the line for the first time into the cache, and therefore these are called compulsory misses. So no matter what you do, you are going to incur these misses once, and a compiler may not be able to do much except if it does something like a prefetching, which we will skip here. Okay. Now, if you are repeatedly executing this loop for whatever reason it is, then in the subsequent iterations, you will see that all of this would again now turn into hits. Even these misses would turn into hit, because this entire 2K elements was brought into the cache. It remains in the cache until something else replaces it, and therefore this whole thing would remain in the cache. Therefore, subsequent iterations, if you're again iterating this through again and again, that you will actually get 100% hits. This is the way that you try to analyze it. There are lots of details, and you probably want to go through this little slowly. So I will make the slides available to you. You can have a look at them in detail, right? Now, let me just try to add some complications to this and then say what happens. Supposing, let's say I have two arrays, A of I and B of I. And, now the accesses are going to be in the following way. Here I am multiplying, I'm taking a dot product of these two vectors and then adding them. So my array reference sequence will be A0, B0, A1, B1, and so on. Correct? So I'm going to access these two arrays in an alternating fashion. Now, supposing, let's say that, these arrays are stored in locations 0xA00 versus 0xE00, right? Basically, I'm putting them adjacent to each other. Right? There is a reason for me to do this. You will understand why it is. But if you change the address also, you can redo the calculation. That's not very difficult. Okay. So you can see that the address A00 is going to be divided exactly like this. and the address E00 is going to be divided into the 3 fields like this. Now, what do you observe? You observe that the index bits of A0 and B0 are exactly the same. Since this is a direct map to cache, right, A0 and B0 map to the same location in the cache. So when I try to access A0, I will bring that line into the cache. And then when I try to access B0, I will replace A0 and then put B0 in that location, or put the block corresponding to array B in that location. The next time when I am trying to access A1 again, this block was brought in some time ago, but got replaced by the block from B array, and therefore this is going to be a miss. Similarly, this B array was also brought in, that particular block was brought into the cache, but that got replaced by the A array. So in this case, what you are going to see is that these two arrays, when they are accessed alternatively, because they are getting mapped to the same index bit, correct? The respective elements are getting mapped to the same index bit. You are going to see miss, 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 and again miss. So all your accesses will end up in misses. I think that is what I have shown here as in this diagram, right? Of course, here I have assumed my array size to be only 1023 because that is enough, because 2 arrays each of size 1024, therefore each is totally 8K plus 8K, 16K, that occupies the entire cache. But now what you see here is that when you try to access B0, the first time, of course, it is a cold miss. Subsequently, when you try to access A1, because B0 has replaced A0, A1 will be a miss. Because A1 has replaced B0, B1 will be a miss, and so on and so forth. These misses are called conflict misses, and they happen because these two arrays are trying to access the same location. I mean, they're getting mapped to the same cache block, and one is replacing the other. All right, so what could have we done for this, right? So from a compiler perspective, if you look at it, all that you need to do is to shift one of these arrays so that if A0 starts from index set 256 and if B0 starts from index set, let's say 257, then of course you could have accessed A0 and B0. You could have actually put those arrays in index sets 256 and 257. Then the next 3 elements of A0, A1, A2, A3, as well as B1, B2, B3 would have been hits because they are getting mapped to 2 different locations, right? 2 different locations in the cache. Such kind of things can be done by simply padding one of the arrays, typically the first array, with some additional elements, right? That's really what you see here. If it is 1024, you pad it with another 4 elements to 1028. If it is 256, if it is 2048, you pad it with another 4 elements and so on and so forth, right? So when you do this, actually, they will get mapped to different indexes or index sets, and therefore you will avoid these misses. Again, I will not go into the details. You can go through the slides and then understand it. Another way to do this is to kind of say, okay, you're going to access array A and array B alternatively. Don't try to keep them as 2 arrays, but try to keep it as a structure of 2 arrays. That is, in this case, in this case, what you're going to have is that you're going to have a structure in which you have an A element and a B element, and that structure, right, is going to be replicated multiple times. So you essentially have an array of structures, right, rather than a structure of array. So if you try to have an array of structures, then this structure is called array I, and in that there is an A element and a B element, and these 2 elements now would be adjacent elements. So if you look at your cache block will be filled with A0, B0, A1, B1, and so on, right? Those 4 elements would be there, and that's another way of doing this. So there are many ways by which you can actually provide compiler optimization to achieve this. Again, as I said, I will not go into all the details. The slides probably have more details of them, and then you can also go back to the textbook and look at them. Let me just conclude this discussion by talking about matrix, accessing a 2-dimensional matrix. So in this very simple example, I'm basically doing addition of Aij and Bij. And when you talk about the reference sequences, essentially the accesses are to A00, B00, and then of course you are storing the result in B00, then A10, B10, and so on. Note that the for loop is like for j is equal to 0 to 1024, and then for I is equal to 0 to 1024. So the I loop is the one which is varying faster. That's why the first index is varying faster, right? That's what you can see here. Now, of course, you need to ask, this is the access sequence, that is fine, right? These are the references that are being made, the accesses that are being made rather. But how are these arrays stored in the memory? So this is where we talk about what is called the row major order and the column major order. And in the row major order, consecutive elements of the same row are stored in consecutive locations, whereas in the column major order, right, elements of a single column are stored one after the other. The first one is used in C language. The second one is actually what is implemented in Fortran language. So if you now look at your loop and then try to see your accesses, right, these are your accesses, you can see that you are essentially going through column by column. That means you are accessing all the elements in a one column and then going to all the elements in the other column and so on, right? So when you do that, essentially what happens is that each one of these, let me just take my pen here, right? So roughly speaking, this would be one cache block, right? And you access one element of that cache block. Then you try to access the next row. Then you bring in another cache block and you access one element and so on. And then again, if you try to come and then when you try to access this particular element here, you can see that this cache block that you brought in some time ago, if it is there in your cache, you will get what is called a temporal reuse, right? Because this was accessed some time ago, you are trying to access it, right? But sorry, this is not a temporal reuse. What am I talking about? I'm sorry. This is a spatial locality, spatial reuse, but happening after a long time because you are going through all the other elements of the column and then trying to access this, right? So when you try to access this, if this block is there, you will get that spatial locality and the spatial reuse. If the block has been replaced by any of these blocks over here because this array is large, then that spatial reuse cannot be exploited. This is the problem when, in a C program, when the arrays are stored in the row major ordering and you are trying to access them in the column major ordering, right? When you access them in the column major ordering, you are trying to exploit spatial locality, but that spatial locality is lost because some time ago you replace one of those blocks with a block in the array. Okay, the same thing could happen for B, and therefore you could really end up in having a lot of misses in this particular example. So what you do is that you reverse the order in which you try to access them. You access them, instead of accessing them column by column, you access them row by row. That means access all the elements in the row first and then go to the next row and so on. Thereby you can actually exploit spatial locality. Of course, you have to make sure that array A and array B do not map to the same index or the same set, because if they map, then also you will have a conflict. Okay, so this is all about that and some level of detail here. I'm going to skip them, but if you do the accesses in the right way, then you can actually get a very high hit ratio. You can actually improve the hit ratio from 33% all the way up to 83% or so. Okay, now let me stop here for a minute, and if there are some questions, I will take them. Otherwise, I'll spend the next 5 minutes on data parallelism before I move to register allocation. Okay, so here what I wanted to do is that I want to quickly give you an introduction to data level parallelism, because in the last lecture we are going to talk about vectorization and parallelization. So vector processors essentially try to exploit what is called single instruction multiple data. That means that they want to perform the same operation on multiple elements of the vector or multiple elements of the array, right? There are two ways of doing this. One is called vector processing, the other is called array processing. So one is called temporal, the other one is spatial. We don't really need to worry about how exactly they get executed in the architecture, but the essential idea here is that you are applying the same operation on different elements of the array. For example, let us say that you want to scale a vector by a value. You want to scale a vector by a value 2. Then that essentially means that each element of the vector is going to be multiplied by 2, right? You can actually do this for all the elements of the array in parallel, right? This is essentially what is called a single instruction multiple data, because the operation that you are performing is multiply by 2, and you are performing it on all the elements of the array, right? And this is possible in modern processors. You may not necessarily do it for all the elements, but you will do it for more than one element in a single go. For example, you can do a set of 4 elements together, or a set of 8 elements together, or maybe a set of 64 elements together, right? And this form of instruction is what we call as the multimedia extension, or advanced vector extensions, and so on. This is called the streaming extensions, and so on. So there are different versions of this, and they essentially try to address this array parallelism, or vector processing, so to say, on multiple elements of the array together, right? So you could see that in your x86 processor, you have different AVX instructions available, right? Today we talk about AVX2, AVX512, and so on and so forth. That essentially allows you to perform these operations on maybe, let's say, 8 double precision floating point numbers, or 16 single precision floating point numbers together, or maybe even larger, 32 4-byte words together, and so on and so forth. Okay. You also have this kind of a parallelism happening in graphics processing units, when multiple threads in a warp work together on different elements of the array, right? So if you again look at it, AVX, array processing, vector processing, graphic processing units, they all try to implement what is called SIMD parallelism, single instruction multiple data parallelism, implement it in different ways, and implement it to different extent, how many of them they can do in parallel. For example, in a graphics processing unit, typically each streaming multiprocessor would actually execute this operation on 32 elements of an array, right, together, and so on. So again, this goes into the same details. You can see that how this has evolved over the years, starting from 1993, when multimedia extensions were first introduced. Okay, it was 64-bit width, and today we talk about AVX512, which is 512 bits width. And if you think of 512 bits, that's essentially 64 8-bit operations, or you can think of it as 8 64-bit operations, 8 double precision floating point operations. So that's essentially what it is, and this diagram shows how it has evolved over the years. So what really happens here is that you take these multiple elements of the array and you perform operations on them, and then you store the value back into the multiple elements of the array. Here, for example, I'm doing an operation like x of I plus y of I, right? And then putting it into z of I. So I take the corresponding elements x0, y0, x1, y1, x2, y2, and so on, and then perform the operation and put the result back into these vector registers. So these machines which support these AVX kind of instructions have what are called vector registers, which are wide in the sense of, for example, when I talk about AVX 512, these vector registers could be as wide as 512 bits, and therefore can hold 8 double precision floating point numbers, or 16 single precision floating point numbers, and so on. And I can perform different kinds of operations on them. I can do data movement operations, bringing them from memory to these vector registers, or I can perform addition operations between two vector registers, or I can perform logical or other kind of comparison operations, or I can convert from integer to float, or float to integer, and so on and so forth. I can also do them data movement operations like shuffling and so on with these things. Okay. In an AVX 512 processor, in a processor which supports AVX 512, you have actually 3 sets of registers. One which can actually hold up to one set of registers, the Z register, which can hold up to 512 bits. And then for compatibility and other reasons, you also have the Y registers, which can store up to 256 bits, and then of course the X registers which can store up to 128 bits. It doesn't matter, in each one of these sets of registers you can actually perform multiple operations together as vector operations, and that's really what is important over here, right? Again, this goes into how these things are divided into different number of different data types. Okay, so before we conclude this, what do we really mean by these vector operations, right? As I said before, for example, let us say I want to find y of I is equal to x of I multiplied by y of I, right? Or if you want to, yeah, okay, or if you want to think of this more like, instead of y of I, let's maybe think of this as z of I, right? Even better, right? So basically we have three vectors, x, y, and z. Z is essentially the pointwise product of x and y, right? Let's look at how these AVX instructions would look like. So for example, this first instruction here moves certain number of elements from the memory, right, starting from the x location, x of 0 or x of 64 or whatever that you want to talk about, into the x register. Similarly, this will do the move from the y array into another x register, and this would essentially do the multiplication, pointwise multiplication, right, taking elements from xmm1 and xmm2, doing the multiplication and putting the result in xmm0. Then this will actually move the value back into the z array. Then you keep doing this. In this particular example, I have taken the x register and I am doing it on the x register. If the architecture supports y registers and z registers, you could have used them and you could have done many more operations together in parallel, right? A compiler like GCC can actually do this vectorization on some simple loops, and these are the flags which would enable you to do this automatic vectorization. Or the programmer can write vector intrinsics in his code and then he can parallelize the code. Or one can develop some sophisticated compiler techniques which can take care of even more complex loops and then try to vectorize them, right? So just want you to have this idea that when you have computations of this form, right, you can actually vectorize them and then perform. So what does it mean to say vectorize? In this particular example, let's say that we are performing 16 operations together. So if I have an array of 256 elements, right, if I don't do vectorization, then I have to iterate this loop, right, 256 times. But when I vectorize it, right, I have to iterate this loop only 16 times, and in each one of those 16 iterations, 16 parallel operations are being performed, right? Here I am moving 16 array elements into x register, 16 array elements y into another x register. I am performing 16 multiply operations. I am doing 16 stores back, right? So that's the advantage of doing vectorization. And on simple loops like this, you can do vectorizations and get the benefit. And typically, the compiler is able to detect where it can be vectorized, and it generates the corresponding vectorized code. Okay, I think that's all I have. If you have any questions on this last aspect, maybe you can spend a minute or two. Otherwise, I will move on to register allocation. Thank you.